Welcome to ZS Robotics.
Welcome to ZS Robotics. Today is a physics lesson.
Let's get physics.
Newton's first law. An object in motion will stay in motion unless acted upon by an external force. Go in motion. Now he's staying in motion and external force.
Ow.
And he stopped.
It's so dead.
Newton's second law is the equation for force. Force equals mass times acceleration.
We gotta remember, force is proportional to acceleration. So when acceleration is raised, so is the amount of force.
Here's a practice problem for Newton's second law. Now Newton's second law states that force is equal to mass times acceleration. Now say you have a problem that states a car is accelerating at a rate of 2 meters a second and weighs 3,000 kilograms. What is the net force required to accelerate the car at 2 meters a second? Well, it's really easy. So to find the force, you simply multiply the mass, which was stated as 3,000 kilograms, and the acceleration, 2 meters per second squared. You multiply these two together, and you get 6,000 kilograms per meter per second. Kilogram meters per second squared. That is your force.
The third law is the law of two systems. For every action, there is an equal and opposite reaction.
So what you have to remember here is the force exerted on the ball is the same amount of force exerted on Daniel.
Practicing it.
Mechanical Dan here.
Doing it.
Where'd he go?
Stop filming. Stop filming.
Now it's time for systems of particles and linear momentum.
So I'm gonna use this steel ball and hit this eraser. Mass.
Quick mass!
To solve this problem, we have the eraser. Let's assume that's 10 grams. Then we got the ball. Let's assume that's 100 grams. The ball had an initial velocity of v naught. That's the official. After the collision, it had a velocity of v naught over 3. Now we've got to solve for change in kinetic energy. The formula for change in kinetic energy is delta Ke equals Ke final minus Ke initial. The formula for kinetic energy is 1/2 mv squared. So the formula for the final kinetic energy is going to be a little different because this was an inelastic collision.
An inelastic collision is a collision in which kinetic energy is not conserved due to the action of internal friction. However, inelastic collisions still obey conservation of momentum, which is why we can still find velocity.
We have two different masses. So let's call this mass 1. So let's say this is mass 1, and this one is mass 2. Mass 1 with a velocity of v naught over 3. Oops. Minus mass 1
Yes, he made a mistake. He'll pick it up in a second.
with this velocity, which is unknown. The initial kinetic energy is going to be the same way, except at this time, this M2 has 0 velocity, so this is just become 0. So it's just going to be 1/2 M1 v naught over 3 minus 1/2 M2 v final minus 1/2 M1 v naught. Wait, what is this final? The final velocity of the eraser is 2/3 the initial velocity. That is because if you add these two together, it equals just the initial, because they add up to 1 total. 3 over 3. Interesting.
be dun, 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 dun.
Dun, 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 dun.
Come on, folks.
So we got 6 over. Now it's just basic algebra.
Once you guys get that pattern down, I can show you the variations that you guys on the
But you can combine these two because these both have the denominator of 2. So it'd be m1 minus m1. And that is. Oops, hold on. Let me erase that.
There's a D string.
Yep. So from the third string down.
Now what we're going to do here is we're going to multiply this all by 3. So we can combine the 2.
This string is in the.
So that's an A. No, you're doing good at remembering that. Like, that's something that took me a while, was remembering.
Now we're just going to combine them all. We can take out this. These will cross out.
Don't so much think about, what not to play in it, because when
This
you're
is
playing it,
very
it'll
interesting.
sound like relatively good. Just like keep it in the back of your head that it's not played in it.
1. Those will cross out.
Are you familiar with the song itself?
So you get.
So,
That is the change in kinetic energy. Congratulations, you did it. This may be wrong. Don't trust me.
This is our final to say that.
Next on the center of mass. Zach doesn't really get it.
The center of mass is considered the average mass. I don't know how to explain this. The center of mass of an object is where the weight is distributed in a The center of mass of an object is where the weight is equally distributed throughout it. So the weight of a hatchet is going to be right off. So this is where the center of all this weight is. And a sphere is going to be right in the center of the sphere.
Okay, this is sort of right. It's more or less where the object will rotate around when it's spinning. For example, when you throw a hatchet, it doesn't actually spin at a point on the hatchet. It spins a little bit below the handle, which is what the point's there. If you spin a ball like a basketball, the way it spins is directed towards the center of mass, which is directly in the center. Zach's a little bit confused.
But in a system of 2 objects, for example, 2 spheres, the center of mass will not be in the center like this. It'll actually be in between them.
we're just too far.
Unless their masses are different, where it would be towards the larger mass.
Say this is a 2 and this is a 1. Now the center of mass will be closer to the 2 than the 1. There's more mass in the 2.
If these masses were equal, 1 and 1, and they were to collide at one point and bounce off separately, so they would go this way and have the same velocities, everything in the system would be the same, their center of mass would actually go along this point where it is equal distance between them. Because this is where the weight is distributed between the 2. Momentum. Momentum is P equals mass times velocity, mv. And the change in momentum is impulse, J. Momentum is also equal to the integral of the force relative to time. This is true because the integral of acceleration is velocity. So if you integrate ma, you'll get mv. Interesting.
So Zach made a little mistake here. The integral says f of x. Now the x there isn't actually necessary. You only need the f because the f is the force. So the integral is the force relative to time. You see, he put that f of x there because he's in calculus and he's a little bit tired. It's finals week. And now for the final piece of the puzzle. Conservation of linear momentum. Conservation of linear momentum expresses that a body or system of bodies in motion retains its total momentum. So, for example, as you can see, Zach here is hitting the hockey puck. When he hits the hockey puck, the momentum of his stick continues, as well as the momentum of the puck keeps going, even if it may not seem to. In a system such as Zach's garage here, there are no external forces, so the momentum is always conserved. So Zach's momentum when he's going around and swinging his hockey stick is conserved, and the momentum of the puck moving around is also conserved.